I say I study physics, I think what often comes to people's minds is the lone scientist at their bench or Galileo and his telescopes. But nowadays, that's less and less the case. We're very firmly in the era of big science, huge budgets, large instruments, and a lot of scientists. I'm a part of the LIGO collaboration, which is the Laser Interferometer Gravitational Wave Observatory, and it's made up of two 4-kilometer long interferometers and thousands of scientists. Big science doesn't always look at big things, but LIGO does. Its goal is to observe the universe, and black holes in particular. Why black holes? Well, when they collide, they give off gravitational waves, which give us information about the universe and its early life that we just can't get in other ways. So, having firmly established us in the realm of big science, I want to scale things back a bit. I'm a microscopist. I deal with very small things. One of the most important parts of LIGO's interferometers are its mirrors, and my field of study is the coatings of those mirrors. Kind of like my glasses have anti-reflective coatings, the mirrors have coatings that make them, well, better mirrors. Everything in your interferometer contributes noise to your final signal, and simply put, noise is bad. You want to eliminate it where you can and understand its source where you can't, so you can account for it when interpreting your observations. Reducing the noise makes the interferometer more sensitive, so it can observe more of the universe. I want to fully understand the structure of those coatings I mentioned, because when we understand the structure, we can work out what noise they produce. So, several years ago, people noticed that there were lots of little holes in the coatings, and a few years after that, another group realized that there was argon trapped in the coatings that just wasn't supposed to be there. So, we stuck the coatings in our microscope to take a better look. Now, our microscope isn't an optical microscope, but an electron microscope. So it shoots electrons through your sample, and when they come out the other side, they might not be going in a straight line anymore, and they'll have less energy than they started with. This will tell us what elements are in our sample and how much of them there are. What we discovered was that the holes in the coatings weren't holes at all, but rather bubbles of argon that had gotten trapped while the coatings were being made. I could count the exact number of argon atoms in the bubbles, and a lot contained less than 100 atoms and was smaller than 5 nanometers wide, so incredibly small. From that, I could calculate the bubbles' densities and their pressures, and other people can take those findings and work out how the bubbles affect the noise in the detector. Now, that might sound like a ridiculously small component of LIGO, but I want to give you some perspective. LIGO was first switched on in 2002, but in 2010 it got taken offline for 5 years. During this time it went through a lot of upgrades, including improving the coatings. When it got turned back on, it made the first ever observation of a gravitational wave within 2 days, proving that the success of big science really does rely on taking care of the little things.